In this video, we'll look at USB Type-C power delivery basics and how to easily incorporate USB Type-C power delivery into your own designs to get up to 100 watts of power into your hardware. We'll do a walkthrough of this USB PD board I designed, featuring a USB Type-C connector, PD controller IC, companion microcontroller, and DC barrel jack for output power. At the end of this video, we'll do a brief test and demonstration of this board using an electronic load. In a future video, we'll look at how the companion microcontroller can talk to the PD controller via I2C to set up and read various PD parameters. What we'll be seeing in this video is the whole schematic for this USB-C power delivery demo board, including a USB-C PD controller, companion microcontroller, as well as some power circuitry. We'll go through all of this in detail and how you can add USB Type-C power delivery into your own designs. I'll also walk you through the design of this two-layer board, showing how we can accommodate this Type-C PD controller, as well as the companion MCU, and what we need to pay attention to when using USB Type-C PD in your own designs. Thank you very much to Altium for sponsoring this video. I designed the USB-C PD demo board completely using Altium Designer. If you'd like to give Altium Designer a try for yourself, also thereby supporting the channel, please check out the link in the description below, or go to altium.com/YT/Phil's Lab, and you can get yourself an Altium Designer free trial with Altium 365, as well as 25% off your first license purchase. To help you get started with Altium Designer, I also have an Altium Designer complete walkthrough, which is almost a 3-hour-long video going from project creation to ordering your own STM32-based PCB, and that's video number 41 on my channel. Typical USB connectors such as micro B, A, and so on only have a few pins. We have power, which is normally at 5 volts. We have our data differential pair, possibly an ID pin in the case of micro B for USB on the go if you want to act as a host or device, as well as a ground, and then of course a shield. With USB Type-C connectors, however, we're adding quite a few different pins and connections. We still have our USB 2.0 data line. In certain cases, we might have a USB 3 connection with super speed. Since we can flip the cable 180 degrees and still have the same functionality, of course we need the pins mirrored as well. For USB-C PD power delivery, what is important are these CC or communication channel pins. Through these pins, which are separate to the data pins, separate to the power pins, we can negotiate power. This is both talking about if we're a source or if we're a sink of power. In this video, we'll be requesting power for a device using the communication channel pins, utilizing some very cool and really easy to use controller ICs, where all of the work is pretty much already done for us. I won't be going into too much detail regarding USB Type-C and USB power delivery. There are many resources on the internet, and I'll leave a couple links in the description below if you'd like to read a bit more, but I'll give you the absolute basics in this video. As there are various data and bandwidth specifications for USB, for example USB 1 low speed full speed, or up to USB 3.1 super speed, which give you maximum transfer rates for data, we have a similar set of specifications for various power delivery or USB power protocols. If we scroll down in this Texas Instruments app note, typical USB 2.0 spec gives us a maximum voltage of about 5 volts and a maximum current draw of about half an amp, giving us a total of only 2.5 watts. Subsequent USB specifications did increase the power capabilities, including one of the first Type-C specifications, Type-C 1.2, where we can get maximum 5 volts at 3 amps, so giving us 15 watts total. What you might have done yourself in your own projects or seen other people do is to utilize that quite simply to get power from a Type-C USB-C receptacle up to 15 watts, so that's 3 amps at 5 volts. We simply need to pull the CC1 and CC2 lines down to ground via 5.1 kilo ohm resistor on each line separately. And so that's a very straightforward way and one of the easiest ways to actually get quite a large amount of power into your device. The question is, what if you want more power from your USB Type-C receptacle and you want to utilize the USB PD spec to get up to, for example, for Type 3.0, 100 watts, or for example, USB PD revision 3.1 added powers up to 240 watts with various different voltages. How do you request, for example, up to 20 volts, up to 5 amps, up to 100 watts, if you want to use that in your own system? It's not quite as straightforward as simply attaching some pull-up or pull-down resistors on the communication channel lines. Luckily for us, people have done essentially the hard work for us and integrated the power delivery protocol within dedicated ICs. And these are typically called USB Type-C PD controllers. These are available from many different manufacturers. many different packages, complexities if you want, for example, a source or a sink, different power requirements, and so on. For example, Texas Instruments has a line which you can browse through. If you go to your favorite distributor, such as Mouse or DigiKey, you'll find a number of them available depending on the needs you have. The actual USB Type-C power delivery controller we'll be looking at in this video is by Infineon, and it's the CYPD3177, which is a 24-pin QFN package, abundantly available at the time of making this video, and fairly cheap. Those aren't the only reasons I chose this product. The main reason is how simple it is to integrate within your own designs. They provide great reference designs, schematics, and a very useful datasheet, which we'll go through. Looking at the datasheet quite quickly, it supports USB Type-C, PD 3.0, revision 2.0, and this is up to 100 watts. This device easily lets us negotiate various powers using USB-C PD protocol, so we can negotiate various voltages from 5 volts up to 20 volts and currents up to 5 amps. So at 20 volts, 5 amps, we get 100 watts out. We also have various ESD protection internal to the device and some other neat features. Another reason why I chose this device are the integrated I2C blocks. This USB Type-C PD controller, which we'll see later, can work with just simple strapping resistors to set the desired current and voltage, which we request from our host, so to speak, but we can also control the device with a host processor, for example a microcontroller, connected via I2C lines to this device. So we can play around with the PD protocol settings and see what else we can do with this device, rather than just setting voltage and current requirements. The datasheet itself provides a reference schematic, but there's also a reference design board, which we'll look at after this. A lot of the USB-C PD demo board I designed is inspired based on the datasheet and also the reference design. Now, while this might look a tiny bit complicated, actually it's very, very simple to set up. We'll go through this in more detail. On the left-hand side, we have a Type-C receptacle, which has the CC lines, which has a VBus connection, ground, of course the other pins. But we only need the VBus in, where we're getting power from, and the CC lines for negotiating with the PD protocol. The negotiation is handled entirely by the CYPD3177. At the bottom side of this IC, you can see various strapping or pull-up and pull-down resistors connected to various pins, for example called iSync Coarse, iSync Fine, VBus Min, and VBus Max. And as these names suggest, these will let us negotiate, depending on the voltage levels at those pins, what required currents we want and what minimum and maximum voltages we want. For example, we can negotiate 15 to 20 volts or 5 to 20 volts or just 5 volts, and we can negotiate, for example, 3 amps by setting the coarse current or 3.5 amps by setting both the coarse and the fine current, and we'll see how to do that later on. In addition to this very, very easy setup, again, you don't need an additional controller via I2C, you could set this up all just using these strapping resistors, but we do have this I2C interface as well as some other neat features. For example, we have a fault indication pin, which we can connect to a switch, or rather a FET, which controls an LED. So if, for example, our device that's connected to the Type-C receptacle, that's supposed to be providing power, can't provide the required current, or can't provide the required voltage, the fault LED will turn on. In this case, if a fault occurs and we can't get the required current and voltage, there's also a safe power enable, which will then negotiate the default 5 volts at 900 milliamp current, which many USB devices should be able to provide. The main method of getting power into your system, however, is controlled by the set of PFETs, essentially acting as a load switch, and pin 3 of our CYPD3177, which turns our load switch, so to speak, on or off. So if we can negotiate the required current via the CC lines and the USB-C PD protocol, we enable our load switch via VBus FET enable, and this is all done automatically for you by this device. It's incredibly easy to use. Again, if we can't negotiate that, we have a separate load switch attached to the safe power enable pin, which gives us 5 volts at 900 milliamps. Then all that is left to do once you've attached this remaining circuitry is feed this on to whatever subsystem you have, and that requires that power. Other than the datasheet, I'd highly recommend checking out the supporting evaluation kit guide exactly for this IC. Scrolling down to the system overview, this will tell you also in detail how this design or this evaluation kit works, including a very high-level block diagram, essentially the same as the schematic we just saw. This will also tell you about part selection, as well as the strapping voltage and current select resistors. Looking at the table, and these tables are also in the datasheet, for example, looking at the VBus Max and VBus Min pins, again, these set the voltage we want to negotiate from our power source. If we pull VBus max or VBus min low to ground, essentially there's 0 volts in that pin, we get VBus min or max negotiated at 5 volts. If we pull it high to 3.3 volts, we get 20 volts. So we can have these set voltages in between depending on the pull up and pull down resistors we have. Similarly, for this iSync coarse and iSync fine pins, again, we're using strapping resistors, pull up and pull down, and depending on the voltage level then at the pin, we get different coarse and fine current values. So we negotiate up to 5 amps and also in steps of 250 milliamps on the fine pin. Therefore, to implement USB Type-C power delivery on your system, for example, using one of these ICs is incredibly straightforward. Follow the manufacturer datasheet, schematics, and part choices, choosing suitable parts, for example, for these load switch FETs, setting your strapping voltages to request the required voltage and current. I'll show you how I did that, including the microcontroller subsection in the schematic now. Here we are in Altium Designer, looking at the schematic of the USB-C power delivery demo board. Keep in mind, this is a fairly simple board just to put on a USB Type-C power delivery controller, a companion microcontroller so we can play with the registers, maybe measure some voltages and currents, so we get a basic familiarity and a baseline system that we can then incorporate maybe into more interesting or more complex designs. It might look a tiny bit overwhelming initially, but don't worry, there's not too much to this. Section by section, on the left-hand side, we have a USB-C connector, we have our USB-C PD controller with surrounding circuitry, an output power barrel jack where we can attach a load to, for example, and then we have the microcontroller section, which is an STM32F401 microcontroller, slightly overkill for the system, but I had quite a lot of them still in stock. To power the microcontroller, when we can't negotiate the required voltages and currents, I also have this VBus, so USB voltage to 3.3 volt buck converter, as well as a programming header, which is by Tag Connect. Keep in mind, this video will focus on the hardware design, the actual looking at registers and talking via the I2C interface between the microcontroller and the USB-C PD controller will be in a follow-up video. Luckily for us, the information we need to design this USB-C PD controller surrounding circuitry is all contained in the datasheet. Although the USB-C PD controller has D- and D+ lines, these are supposed to actually be left disconnected. Therefore, the D- and D+ lines of the USB differential pair I've simply hooked up to the microcontroller, for example, so we can log data through the USB connection to our computer. Following the datasheet guides, we need some decoupling capacitors and bypass capacitors, pull-ups on various lines, and again, this is all taken from the datasheet. So for example, for the SDA and SCL lines of the I2C bus, there's also an interrupt pin, a general purpose input-output, a fault pin, and a flip pin. The flip pin tells us which orientation the Type-C USB cable has. As we said before, the fault pin is simply to drive a MOSFET, which will then light up an LED. I've also hooked up all of these signals to the microcontroller so we can play around with those in a future video. On the left-hand side, we have our VBus max, VBus min, and the iSync setting pins, and again, these are via strapping resistors, taken from the datasheet what values we need. So if I divide 3.3 volts, which is our reference voltage, by 2 using equal value resistors, we get half 3.3 volts on this VBus max pin, and according to the datasheet, that negotiates a maximum of 15 volts. I want the maximum to be 15 volts and the minimum to be 15 volts in this particular case. Of course, it's situation dependent, so I've set VBus min to the same value as well. If you're happy negotiating, for example, between 9 and 20 volts, you would adjust these resistor values accordingly, according to the datasheet. Similarly, for the iSync pins, so how much current we want to request or maximum amount of current, we do similar things again according to the datasheet. For example, if we have equal value resistors, 3.3 volt reference, then we get 3 amps. This is the coarse current. We can do this something similar for the fine current. If we pull this to ground, we're not adding anything with a fine current. The total current requested is the value of iSync coarse plus the value of iSync fine. So we can get increments of 1 amps and 0.25 amps. Moving over to the top side of the circuit, remember we have the Type-C USB connector, which is our VBus, our power input, which also feeds internal regulators for the CYPD3177 PD controller. So nicely enough, we actually don't need any external regulators for this device to function. The VBus in, coming from the USB Type-C connector, is then fed through this FET load switch. Again, taken from the relevant datasheet, we need to size this FET load switch appropriately. So it should be able to sustain at least, plus a safety margin, the maximum current we expect through this. So if you're expecting 3 amps maximum, you should definitely oversize to maybe 5 amps. And make sure to choose a device that has fairly low on resistance so your DC losses and your heating won't be too high. There are various resistors and capacitors you see here, again taken from the datasheet. Some of these will limit the slew rate, for example, but there's also internal slew rate limiting that this load switch turns on slowly and we don't get large inrush currents. Another nice feature of this USB-C PD controller. At the output, I'm then feeding through R19, which is a current sensor resistor. That's why this has a very low value, and feeding to an output barrel jack. Again, with a bit of capacitance at the output. The reason I put in a current rate sensor resistor is again for us to play around in a future video so we can do some measurements and tests when we're running the microcontroller. There's a maximum current of 5 amps for this part, so for a 12 milliamp resistor, I'm getting a 60 millivolt drop. To then amplify that to an ADC range, my microcontroller is running off 3.3 volts, we need to add a current amplifier. And there's these pre-packaged parts, for example, the INA 180. They come in various gain values. The gain A3, indicated in the name, gives us a gain of 50. So for a maximum current of 5 amps, we get 60 millivolts, times that by 50, we get 3 volts, which is a great range for our ADC of the microcontroller. Which then also brings us over to the microcontroller. It's an STM32F401 microcontroller, typical bypassing and decoupling at the power pins, and I've enabled pins we need, for example, I2C, a serial wire debug for programming, USB differential pair, and various signals coming from the USB-C PD controller, which you can play around with later on in a future video. Again, I've also enabled 2 ADC channels. One is to measure the output voltage at V connector, which is at the output DC barrel jack. Again, dividing that down because the maximum voltage might be 15 volts or 20 volts, so dividing that down to a suitable ADC input range. And ADC 1 channel 2 is again used for the current sensor. Got a status LED, an external crystal for more accurate timing, and that's about it. So very, very simple. For programming, I'm using a serial wire debug header by TagConnect, which are my favorite headers to use for programming, and I'll show you a bit more about them when we come to the PCB design. You might have already noticed that I'm not actually using this safe power enable. This safe power enable turns on a load switch if we can't negotiate the current and voltage we set at these strapping resistor pins. The fallback voltage will always be 5 volts and the current should be 900 milliamps. In this case, I didn't really need it, I'm not using it, therefore I'm just sending the pin, which goes high or low, to my microcontroller. Not really necessary in this case, but if you want to implement fallback voltages, keep this in mind that you'll need an additional load switch. Because I want the microcontroller to be on all the time, and I don't want to switch between 2 different load switches, I'm attaching a switching regulator directly to VBus at the USB-C connector, which is a simple switching regulator, which gives me 3.3 volts for my microcontroller. So it's always on regardless if I'm using a Type-C capable power source or not. You might have also noticed that I'm using many of the same value resistors and capacitors, so I have 20 kiloohms and 28 kiloohms in parallel rather than just using 10 kiloohms. And this is because I've done fairly strong BOM consolidation. I don't want a very large bill of materials. Where I can, I'll try and combine resistors together so I only have a couple resistor values. In total, therefore, I only have 2 different types of resistors in my schematic, 2.2K and 20K, and very similar for capacitors as well. I only have 3 types of capacitors in my design, 100 nanofarads, 4.7 microfarads, and then unfortunately for the crystal, 10 picofarads. Keep in mind also as a final note, this is a demo board. You might have noticed there's no ESD protection or filtering on any of these lines because we really don't need to do this for this board. The STM32 as well as the USB-C PD have sufficient ESD protection for this just being a demo board. Also, you could probably optimize a few things a bit more, but for our purposes, just demonstrating how you can include USB-C PD in your own designs, this is sufficient. Now let's move over to the PCB design. The USB-C PD demo board is very, very simple. It's a 2-layer board with components just on the top layer. On the left-hand side, we have the USB Type-C connector, essentially our power input. On the right-hand side, we have our DC out barrel jack. First of all, let's look at the Type-C USB controller, which is this QFN package in the center here. We have our strapping resistors and various pull-up and pull-down resistors all around the perimeter on the right-hand side, and it's definitely not critical how you route these. Of course, it's nice to keep them close and somewhere on a grid, so it looks a bit prettier, but any way you route this is probably fine. The critical sections in quotes are, so to speak, on the left-hand side, which is our power input. You can see I've used very wide traces and planes even, coming from my VBus pins on my Type-C connector, as wide as I can with a space available, and routing through a bypass capacitor or filtering capacitor into this dual MOSFET. This dual MOSFET, as we saw in the schematic, is our load switch, and these are back-to-back P-channel MOSFETs. So as wide as we can connections to sustain, 3 or 5 amps of current, depending on what you've set up, depending on your stepping options, for example. Again, this is very much design dependent, so you can get away with thinner traces if you're only getting up to maybe 2 amps, and so on. You also might notice that there are no thermal reliefs on this design, and given the small amount of copper comparatively, and that we don't have too great copper imbalances, that this board was reflow soldered, you won't have any problems with not having thermal reliefs, and that's what I found from many boards of experience. Where I have to neck down, I neck down only briefly, so I decrease the width of my trace or planes, and as soon as I can, I increase the width of my planes as well. Same goes for the output, so to speak, of my load switch, my 2 MOSFETs going to the connector. I'm trying to give myself a very wide trace and plane. If we measure the trace width or the plane width of this current carrying plane and trace for my USB-C PD voltage, which could be up to 5 amps at 20 volts, the question is, how do we arrive at this number? Why does it have to be this wide, and how wide can it be or can't it be? For this, I like to use what's known as an IPC2221 trace width calculator based on the IPC2221 standard. Here we can calculate the required, for example, copper thickness and trace width for given currents and temperature rises. So for example, my maximum current might be 5 amps. My thickness of the copper, typically for an outer layer, is 1 ounce per square foot, or 0.035 millimeters. My ambient temperature, room temperature, might be 25 degrees. And of course, I can play around with trace lengths if I want to see what DC voltage drop I'll have. But for actual current handling capability, what's most important is the width and a given temperature rise. If I allow, for example, only maximum 10 degree temperature rise, so up to 35 degrees total, we can see actually for an external layer, so what we're having in this board, we only need a trace width of about 2.8 millimeters, and an internal trace might have to be 7.2 millimeters. If we allow for a 25 degree temperature rise, we can get away with an even thinner or narrower trace at only 1.6 millimeters. And keep in mind, 5 amps and 1.6 millimeter thin trace, that trace is tiny. However, even for a 10 degree temperature rise, and that we only need about a 3 millimeter wide trace, to minimize the power loss because of the DC resistance, I'd like to make my traces wider than they need be according to this calculator. That's why this trace is about 4.1 millimeters wide. Keep in mind, again, necking down is not a problem as long as those necks are kept fairly short. Thermal reliefs I've only really added on very small pads or very small components, but for these larger components where I have a better copper balance, I will not do thermal reliefs. Other than the current carrying traces, of course, this goes through this current sense resistor, which was this 12 milliohm resistor, and we also have our current sense connections. Going to 2D view, looking at those, we have our wide current carrying traces, but we also have these thin traces going into my current sense resistor. This 4-wire connection is what's known as a Kelvin connection. 2 traces for current, and we have 2 traces for voltage. These are voltage sense traces, short traces, fairly thin traces, because they're not carrying any current, which goes straight into my current sense amplifier, and then that feeds my microcontroller ADC. So keep in mind, wide traces, use the IPC2221 calculator, and oversize your traces as far as it allows. Watch out for thermal reliefs, maybe on smaller parts, and where the copper balance might not be as good. Other than that, the usual recommendations apply of having your decoupling capacitors, keeping the loop area small, close, but not too close to the IC. Not too close meaning you won't get assembly problems or debugging problems, but close enough so you minimize inductances by minimizing loop areas. You might also want to space your resistors out a bit more in case you want to switch out to different voltages and current settings as well. You could, of course, also make these resistors variable, or digital potentiometer. But we'll also look at, of course, how we can control this USB Type-C power delivery IC using I2C. Other than that, the remaining board is equally as simple. We have our STM32F4 microcontroller hooked up with short traces to the I2C lines and so on. We have the usual decoupling capacitors, close to power and ground pins, minimizing loop areas. Some bulk capacitance around the board, our crystal oscillator in its own little section, kept away from any high-speed traces, not that there are high-speed traces in this design. The usual recommendations apply. For programming and debugging, you might have noticed this header, or rather this solderless header up here, and this is this tag connector I've been talking about before, and my preferred method of debugging and programming pretty much any device. With tag connect headers, you don't need to solder on any headers, you just need this adapter cable which plugs in, for example, for STM32 microcontrollers to your ST-Link or to whatever debug tool you're using. So you save costs on every board, and it's a very small footprint. I'll leave a link to these in the description below, but these tools I really recommend, and I'd suggest you check them out for yourself. In any case, this tag connect header simply has the serial wire debug lines routed with fairly short traces to the microcontroller. Then of course we have a switching regulator, which is laid out as switching regulators should usually be, which is small loop areas, tight layout and tight routing. Switch node, for example, only as wide as it needs to be, the feedback network away from the switching element, and so on. If you're interested in more detail on switching regulator PCB design, I'd highly suggest checking out video number 60 on my channel. Since this is a 2-layer design, my bottom layer is simply a ground pour. I had to do quite a lot of cuts in the ground plane below, which I don't really like doing for 2-layer boards as it really disrupts the reference. But then again, you're not going to have a great reference anyway for 2-layer boards, plus this is a demo board, so it's fine to do this. This is not going to have to pass any sort of MC testing or anything like that. For functionality testing, just demonstrate USB-C PD. This is a very, very straightforward board to lay out and route. And as you saw, the centerpiece IC itself is very, very easy to integrate within your own designs. Now let's go over to the real world, so to speak, and test out this device with an electronic load. Remember, the fallback voltage is not actually implemented on this particular demo board. So if I just take this USB-C connector, which is just hooked up to a normal USB-A port on my desktop computer, so not USB-C PD capable, we'll see we actually can't get the PD section to run. Of course, the microcontroller will still run because the buck regulator for the 3.3 volt supply is hooked up directly to VBus. So plugging it in, you can see you have to wait a tiny bit for the USB-C PD chip to try and negotiate, but then the fault LED, this red LED at the top here, turns on, indicating we couldn't negotiate the required 15 volts at 3 amps. Remember, my desktop PC, my USB-A connection is not USB-C PD capable, so it can only deliver 5 volts at a significantly lower current. I've now hooked up the USB-C PD demo board both to my phone charger, which is USB-C PD capable up to 100 watts. That's going via a USB-C cable straight to this USB-C PD demo board. And from that, I've attached this DC barrel jack connector, just cut off the loose wire ends. This is quite a thin cable, especially given the amount of current we're trying to pour through it. We can expect quite a bit of DC resistance and therefore some voltage drop at higher loads. Then I'm using my Rigol DL3021A, which is a DC electronic load. And from here, we can see what the voltage is at the output. Of course, we have to take into account the loss from the cable and these rather thin wires. And we can play around with various loads, see if we can get up to 3 amps, which is what this board is set to, see if we can go lower, and see if we can even go higher than what we are requesting at the moment with these various pull up and pull down resistors. So turning on my load, I could of course also attach these sense cables so I can measure directly at the point on the board to get the accurate voltage at the output, but I'll just be using a normal DC multimeter instead, just so we can probe around a tiny bit. So with my DC load on, we haven't got the power supply plugged in yet. I'll plug the power supply in now just to a wall outlet. I've now plugged in the power supply, my phone charger via USB-C cable to this USB-C PD demo board, barrel jack as before going to the load. We're currently not drawing any current, any power, and it's just measuring the voltage, not via the sense terminals, but rather the input or load terminals. We're getting exactly the voltage we negotiated for. Again, that's simply using those pull down and pull up resistors. We could, of course, in a later video, we'll see that, configure things via the I2C interface connected to, for example, this host microcontroller. What we can do now, I've set it up so we can draw about a ½ amp of current, and so you just start with that. I just turn my load on and we're drawing a ½ amp. You can see there's quite a considerable voltage drop. Again, it's this very thin pair of cables here are adding considerable DC resistance, and therefore even at ½ amp, we're getting about 0.4 of a volt drop. I just measured with my multimeter. I've got my hands a bit full, so I can't show you, but I'm getting about 14.8 volts directly at the DC barrel jack. Okay, so let's slowly start cranking this up, see what currents we can draw, and again, because of these pull up and pull down resistors, we should be able to draw up to 3 amps of current. So let's just slowly edge up. Let's try with 1.5 amps now, so I'll just enter that in the keypad, press OK. And keep in mind, this voltage drop again is due to the rather thin cables here. But we're getting 1.5 amps at about 15 volts given the DC voltage drop. So of course we could do with better connections as well. Let's try and turn that up a bit more. You can see we're getting 21 watts approximately now. We can turn that up, let's say to 3 amps directly. Press OK, and I'll just turn on the load again. And we'll get quite a considerable voltage drop, of course, again, the DC resistance. But we're drawing 3 amps, which is great. In terms of thermals, just touching the board is slightly warm, of course, due to the MOSFET resistance and also slightly the trace resistance, but it's nothing much above room temperature. So we're drawing 40 watts, so it's pretty easy to get quite a considerable current and power out of USB Type-C using a simple IC. Now let's try and go above, for example, at 3.5 amps and see what this whole system does. Can it even cope with it? Remember, we're only negotiating up to 3 amps. Turn this off, type in 3.5 amps, then turning the load on again. and you can see it's not handling it because we've only negotiated up to 3 amps, and therefore we won't be able to get the supplied current and voltage. Thank you very much for watching this video. I hope it is useful, and I hope it encourages you to try out USB Type-C PD in your own design. Keep in mind, we still have a video to come where we'll be experimenting with the host microcontroller on this board, trying to interface with the I2C to the PD controller IC. So make sure to subscribe so you don't miss out on that video. Thanks again for watching, and I hope to see you in the next video. Bye bye.